final thing. We just a little bit looked at R, but let's look a little bit more at R for what I taught you today. We saw this one already, that there is a function in R called prop.test for testing proportions. You can add a single proportion, or you can in fact add several proportions. If you put severals here and several n's, so you put the x and you put the n, or you put all the x's and all the n's, it does hypothesis tests and potentially confidence intervals. There's this little tweak here, or this wording. There are ways, we've seen one example in this lecture today on how to improve these methods to make them even more valid, or valid even for n's that are not as large as those requirements that I've given to you. There are tweaks to those methods that make them more correct for smaller n's. And the functions in R make many such nice defaults. The default in R, when we do this, actually is to use one of those tweaks, which is called formally a continuity correction. We do not teach you the math details of continuity corrections, not because it's rocket science, but because we have many other things to discuss in this course. So this is just to say to reproduce exactly the formulas that I'm showing you. We would have to tell R, do not do those default extra corrections to make it more valid. When n is really large, it doesn't change anything at all. When n is pretty small, it changes a little bit. And then, of course, the ones with the corrections are considered to be more correct than those without the corrections. I'm just letting you know, for pedagogical reasons, this is how to reproduce exactly what I teach you, right? And for practical purposes, this is fine. Here's an example of two proportions. There are at least two ways to make prop test analyze two proportions. In this slide, I'm showing you how to put those numbers from the blood clot study into a 2x2 matrix, a 2x2 table. I give it some names here. That's not necessary. That's just to make the output look nicer when you look at the results. Then you can apply prop test to this matrix to get the results. Maybe we should just jump into R to see it. Here's exactly the code that I was showing you. Note the two proportions that we had on the slides, 40%, 21%. The confidence interval for the difference, actually. The p-value for testing whether they're the same. They're definitely not the same. And the chi-square test statistic that was on my slide, also 8.33. And it tells us I don't use any of those corrections that I didn't teach you because I asked the procedure not to. We could just, for the fun of it, confirm my claim that if I actually did not add in this, because, well, if I never heard of this, I wouldn't put it in, what would the results be? Yeah, it's not exactly the same chi-square, but no dramatic differences in the results, actually. If the n was much larger, we wouldn't see any difference at all. Good. Actually, the prop test, let's see if I could do this. As always, dangerous. I could have added in 23, 34. Were those the two? Let me just double check my blood clot data. Here we are. Let's look at this one. Yeah, this is, this is 23 and 35 is the response to the number of illnesses, right? So let me see if I can manage to remember. 23, 35, 23, 35. These are the two x's. What are the two n's? This is difficult now. I have it in another slide. The two n's are, the two sample sizes, that's 57 and 167, right? 57, 167. 57, 57, 167. Let's see if that gives me... Yeah, look at that. So I could give the two x's and the two n's, and I get exactly the same result. It's just two different ways of providing the numbers to the same function. Both of them works. I could also have... Let's go... Panic is coming up, but let's see if we can keep it away for just 2 minutes more. Here is the general function for the chi-square testing that works for any kind of frequency data table. It's called chi-square test. It's as fundamental as the t-dot-test. There's a chi-square-dot-test. You plug in a data matrix, a 2x2, 3x3, 5x7, 20x30, whatever dimension, frequency table, and then you can look at the results. You can extract the expected values, and you can look at the percentages. You can get the chi-square values. Let's have at least one look at that. Hope we have an example. Chi-square test. And if I just do the chi-square test, and again there is the same about this continuity correction. Now I put in the false, so I reproduce exactly the formulas I've shown you in the book and in the slides today, and you can see I reproduce my chi-square test here, which is exactly the same thing. You could save the results and check the expected values if you want. Here I save the results, and then the function itself actually remembers. It has a name for the expected value. So if I want to check for myself, are those expected values all larger than 5? If I didn't believe that the function would warn me, let me go check. And yes, they're all larger than 5 in this case, so fine. We could, just for the fun of it, what happens if we go, just say, 24, 30, 40, that would be something where we have, I'm just playing around with the numbers, and look at this. I only had 23, 1, and 35, 5. So it's a very sparse in the one column. And overall, the expected values now, warning message, chi-square approximation may be incorrect because the expected values are becoming too small. So it gives us a warning here. In this case, a nice friendly function. That's related to the assumption or the requirement. We're almost there. I'm not going to spend time now. You can see the other examples with the poles and the 3x3 tables. It's running exactly the same way. Plot percentages. Let's not do that. I want to show you that I did put in these that's in the materials page or the content page. I have these malformations data from the report, from Sundhedsstyrelsen's report. I put them in a small data set. Which are the different years from 94 to 2005. There are some different numbers that means different things. I checked the report to make sure what those numbers mean. And actually, I have made those numbers into something that tells us that the actual ends those years. Here are the number of births each year in Denmark from 94 to 2005. 69,607, decreasing down to 64,583. 205, I haven't checked, I don't know what the numbers are now. But that's during those 10 or 11, 12 years actually we're looking at here. And also the percentages, and then I basically, from these percentages, I have added, I've reconstructed, and I've shared with you the little code to actually reproduce exactly the plot that was given to us in the report in the beginning. All the proportions with the confidence interval using the formula that I've showed you, and then with the overall mean. And maybe just as a final thing, what do you think the hypothesis test will tell us? Are those 12 proportions different from each other? I mean, the joint P is the blue one. That's the overall P. That's if they should be the same. What's our gut feeling? What's your gut feeling? Is it different? It's different. Yeah, I think so. Because it's really consistently, if you look at the confidence intervals just to have, it's really consistently away from that. And even there is, if you put in a regression line, you could do that. I don't show you how to combine proportions with regression analysis. That can be done. It's called logistic regression. It's one of the core machine learning techniques actually, which is a statistical technique. But nevertheless, if you put in such a regression, it will be significant to, I don't know, it will be strongly significant. However, we can still make a test, as I've taught you. Let's test whether those 12 proportions are the same. I can either do it by prop test, where I have all the x's and all the n's. Here are all the proportions going from 4% up to 5%. What's the p-value? They're pretty different, or they are pretty, certainly they're different. And then we look at what they are to see what's the size of the difference. We get the same thing by chi-square testing. Same p-value, like that. They're different, and it's easily done in R, like that. You can see it all where you are. We're getting there. Last question to get a winner. Well, you'll see what's the right answer. I'm a softie, right? You're all right, of course. It's a personal thing. So if you were fast, you got the points. Let's see who got the idea. So Baguette, good name for today's topic, number 3. Who is Baguette? Do you want to get the applause? Good job, Baguette. And then the real slim guy. Good job there. And finally, the music person, the winner of today. Whoa, first row. Very good job. So enjoy it out there, and I'll see you next week with a bit of recap and overview. I'll send you a message about that. Otherwise, enjoy.